Hello everyone, my name is Vladyslav and I want to present our research simulation platform for testing and validating of UAV visual guidelines algorithms. This presentation will provide a comprehensive overview of our approach for improving process of development algorithms for automated UAV control. This work is a part of our project to develop UAVs with automated targeting and is the result of our finding a way to optimize this process. So let me introduce our team. There are 5 people are working on the project. Kostiantyn Dergachov and Iryna Bychkova are leads of our project and 3 engineers, Vladyslav Dubinin, Eugene Ovdiyuk and Puhach. Before we begin reviewing the system, I would like to present a list of publications and key sources that served as the foundation of our research and guided the development of our methods. If needed, you can refer them for additional information. And now I think we are ready to start our main part of presentation. Nowadays, such sectors as agriculture, geodesy, security systems, life-saving operation, cartography, and other use different types of the unmanned aerial vehicles for their tasks. However, development and automated UAV control systems requires many resources, both in terms of cost and times. During development, iterative testing of new features is often needed. This can lead to the damage or even complex destruction of the UAV. In addition, testing requires specific environment conditions, such as different lighting levels, fog, and various times of the day. The tasks become more complex when it includes tracking another UAV as a target. This requires operators who can control the UAV and perform planned maneuvers and trajectory. Moreover, an operator can't repeat the trajectory flight path from the previous task to the new, and it making it difficult to objectively evaluate improvements in the tracking algorithms. For this reason, a simulation platform is a logical and necessary solution that helps save resources and improve testing efficiency. During the work on the main project, specifically the development of target tracking algorithms, the team faced a problem: the lack of test data for the algorithm evaluation. As a result, it was decided to create a system for generating video from the onboard camera of a UAV. Based on this, the following requirements was defined: the ability to simulate two flat objects, UAV and target, simulation of onboarded camera and ability to record video from it, and the ability to fly by trajectory. Later, during the improvement of the algorithm and to the testing, additional features become necessary. The ability to control the UAV using scripts, the ability to save and replay flat scenario considering environment factors to ensure consistent test conditions, and the ability to evaluate the performance testing of tracking algorithm. With this list of requirements, the development of software solution to meet them was initiated. A detailed analysis of existing flight simulation software solutions was conducted and their key features was highlighted. It was found that most platforms focused on simulation small quadricopters with limited space for maneuvers, typically indoors or on racing tracks. Additionally, no software solution were found that allows adding an extra flight objects as a target for tracking. The ability to control environment conditions was also quite limited. Most simulations provide only a fixed time of the day and sun brightness for a specific flight map. As a result, it was concluded that no platform currently meets the defined requirements. Consequently, the decision was made to develop such a system independently. As for our technical stack, we choose the Unreal Engine as the main platform. This engine is one of the most popular due to the active community and their ability to realistically simulate physics and environment. Additionally, Unreal Engine supports C++, which provides flexibility and allows integration with other systems. For processing image from the onboard camera, we use the OpenCV library, which offers a wide range of the tool for image and video processing. For writing target tracking algorithms, we selected Python. This choice was based on its easy integration with C++ and support for the OpenCV library. In addition, various 3D modeling tools were actively used to create environment assets and UAV models. So, moving to the system architecture. Our system consists of several function blocks. Environment simulation block. Create a virtual environment that impact on the onboard camera image. Virtual UV. Simulate the physics behavior of the drone including the camera and sensors. Virtual target. Simulate the behavior of the target drone controlled by configurable scenarios. Testing stand. Evaluate the testing of algorithms by running test scenarios. Simulation control block. Coordinates all components, ensuring stable system operation. This comprehensive solution allows us to test algorithms in realistic conditions. Let's take a close look at these systems parts. The environment simulation module provides management capabilities for the virtual world with realistic atmospheric effects, such as changes in lighting, time of the day, fog, and cloud cover. These parameters significantly influence the result on board camera image and the performance of computer vision algorithms. This allows for tuning of testing conditions under specific scenarios. Another important part of this model is creating of the map. Depending on the needed, it can be filled with trees, an urban area with many buildings, or map based on the aerial photographs. Since the camera is located high above the ground and can change the angle during the flight, optimization of the map building process is important. Let's take a closer look at how this is implemented. The approach to optimizing environment using particle environment generation is called frustum culling, but it has been extended to handle significant camera movement with the UV. The map generation process consists of the following steps. When the program starts, the camera radius and type of the map are obtained. Then, at each iteration of the system, the following logic is executed. The position and direction of the camera are determined. If the camera position and direction haven't changed from the previous iteration, no map changes are needed, and the system moves to the next iteration. If there has been a change, the following occurs. Based on position, vector, and radius, the visible area of the map grid is determined. Grid cells from the previous iteration that are now out of the visible area are identified. Objects are removed from the cells that are not longer in visible area. Objects are created in the cells that are now in the visible area in the current iteration. The current iteration ends and the system is ready to next iteration. The next important part of the system is the virtual UAV. It performs the following functions. Change the position of the UAV in the virtual space in response to control signals. These signals can come from both the control algorithms being tested and the operator. Another important part is the simulation of sensors. Currently, a barometer, accelerometer, and gyroscope are implemented. They can be used by control algorithm to obtain additional information about environment. However, the main source of information for the algorithm is the onboarded camera. It is implemented by converting the image from a scene capture component in Unreal Engine into standard matrix format of the OpenCV library for future processing. This slide shows the target tracking process using the algorithm. The upper UV is controlled by operator, while the lower UV is controlled by the algorithm that track the target based on the camera data. The last part of the system we will discuss today is the laboratory stand. It is model for testing the effectiveness of algorithms. It consists of the following elements. The test data manager, which creates the test scenarios with video from the board camera and telemetry data. A Python scripts executor, which allows to running user control algorithms for evaluation. These blocks allows you to analyze and define weakness part in the trajectory algorithm. Currently, two main types of the testing are available. Real-time testing, when the operator controls the target and analyzes how successfully the algorithm can track it. And deep testing. The operator records the target trajectory and environment condition for future repeated use in testing the algorithm to track the impact of these changes on the algorithms. As I mentioned earlier, the system was created as a part of a project for developing a UAV with automated target tracking. The use of this platform allowed not only the create of realistic test data, but also improved the algorithms. On this slide, you can see a comparison of the first version of algorithms with its improved version. As shown in the plots, the algorithm has significantly improved for working in good visibility condition. However, it's clear that the algorithm effectiveness at night still requires additional improvements. Also, the system allowed to notice that the improvements in the algorithm effectiveness lead to the increase in the processing time of each frame in the video stream. This will be taken into account in the future development. Based on this, we can make a conclusion that the flight testing simulation system has proven its effectiveness even on the prototype stage. This system allowed developers to find and fix weaknesses in their algorithms without leaving their workplace and without the need for real flight tests. The system is currently under active development to support complex physics model of UAVs. Plans include detailed modeling of the technical and aerodynamic characteristics of aircraft. This will allow to perform more accurate algorithms testing, taking into account the specific control features of the UAV. So, that's all from me for today. Thank you for your attention, and I will be happy to answer your questions.